Alright, so Bowen demonstrated that minerals crystallize from magma in a systematic fashion. But if all magmas follow this pattern of crystallization, how is it possible that there are so many different types of igneous rocks? Or in other words, how is there any magma differentiation in the first place? Well, it has been shown that at one or more points of magma crystallization, a separation of the components occurs or can occur. One of the ways that this is done is called crystal settling. So that's the first way we're going to look at. This occurs when the first formed minerals, which are denser and hence heavier, will sink towards the bottom of the magma chamber, which makes the remaining of the chamber more felsic in composition. So the pictures kind of show you very well what is occurring, and they have little descriptions that are useful as well. So hence, overall, there is some magma differentiation, where the more mafic, if you would, crystals that formed at the beginning settle towards the bottom of the magma chamber, and then the remaining of it is more silicic. This is also why there are certain magmas that are rich in accessory minerals, as they have not been used for bonding yet. So they remain in that melt that hasn't crystallized yet, and are made up of some of the few remaining ions in the part of the melt. So again, those crystals are going to be things rich in sodium and in potassium, but also any random elements that are floating around that are called accessory minerals. There are two other ways in which we can get that magma differentiation throughout all of the igneous rocks. Both of these involve the incorporation of some sort of foreign material. For example, in near-surface environments where rocks are more brittle, meaning more easily broken, the magma that is pushing upwards can cause the overlying rock to fracture into numerous pieces. The force of the injected magma upwards is often sufficient enough to fully dislodge those blocks and incorporate them within the magma body itself. So this process itself is called assimilation, and as the pieces incorporate into the magma body, they melt as well, and their mineral composition is now mixed with that of the magmas, hence changing the overall chemical composition of the magma body. So, for example, let's assume that the rocks that the magma was penetrating into, was being injected into, are granite. Let's just say that they're granite. But the magma body itself is mostly made out of ions that contain iron and magnesium. So once the rocks that are being dislodged and incorporated into the iron and magnesium, silicon and oxygen mix get melted, the overall chemistry of that magma body is going to become a lot more felsic. So you're going to have a more, more non-ferromagnesian silicate minerals within there as the magma body crystallizes. Another way of incorporating other type of materials is to get magma differentiation through magma mixing. So this may occur during the ascent of two chemically distinct magma bodies, as the more buoyant one overtakes the more slowly rising bodies, as you're seeing there on the picture on the right. Once those two bodies join, a convective flow mixes both of those two magma types, and a new kind of more intermediate composition of magma forms. So if you think of the magma body A being more mafic in composition and magma body B being more felsic in composition, magma body B is rising a little bit faster. It meets with magma body A, and once they mix through convection, the overall composition of the new magma body is intermediate in composition. Okay? So, Bowen's reaction series explains the crystallization sequence of a magma chamber and shows how the compositions currently in place for igneous rocks hold based on that crystallization sequence. but it shows no evidence for any magma differentiation, which we know occurs because we do have many types of igneous rocks, ranging from ultramafic to felsic, and sometimes many types of them are near one another at the surface or even in the crust. So those three processes that we just looked at, crystal settling, assimilation, and magma mixing, help us understand that differentiation. All right, so now we are done with the origin of magma and with magma evolution. Now we're going to look at intrusive igneous rock bodies. So although volcanic eruptions are super cool events, most magma crystallizes at depth. So below, I'm going to show you a few of the intrusive igneous bodies, and also because we're going to cover all sorts of volcanic eruptions and volcanic events in Chapter 5. So when magma rises towards the surface, it typically displaces pre-existing crustal rocks, named host rocks or country rocks. The structure that results from the emplacement of that magma into pre-existing rocks are called intrusions, sometimes plutons. Because all intrusions form far below Earth's surface, they are mostly studied once they have been uplifted and after the overlying rocks have been eroded away. We'll cover erosion on Chapter 6, by the way, but I think most of you know what I mean by eroded. But it may be complicated to, have a reconstruction of the history that brought those events to be, from the formation of those intrusive igneous bodies all the way upwards to the surface, even by studying them at the surface. So in the picture on the slide, there are many different intrusive igneous bodies. Some of them are more tabular, some of them are more massive. So I refer to the ones that are massive as mass, and to the ones that are tabular as tab. Also, some of them cut across sedimentary structures, like rock layers. Those that cut across are discordant, and those that don't cut across are concordant, those that go kind of in between the different sedimentary rock layers. So I refer as discordant as disc and concordant as conch. Igneous rocks include dikes and sills. Dikes being discordant and sills being concordant. Both of these are typically shallow features. Dikes, they tend to serve as a conduit to transport magma upwards, whereas sills tend to increase the thickness as the magma takes that easier route. They can both range in thickness from 1 millimeter to 1 kilometer, and they usually occur in groups or swarms. So in an area you might find many dikes or many sills. And they are typically made of more mafic material, which tends to be more mobile, less viscous magmas, right? Dikes sometimes appear as radiating from an extinct volcanic neck, as we will see during our field trip, for example, and we'll also see it, I think, in a few of the images from Chapter 5 as well. Okay, from the massive intrusive igneous bodies, we have things like batholiths, which are by far the largest bodies of igneous rocks. Typically, they're of felsic or intermediate composition, and they are hundreds of kilometers long and wide, but only about 10 kilometers thick, or even less than 10 kilometers thick. Now we know that batholiths are not one single igneous body, but rather they are a large body made up from many smaller solidified magma injections. Those magma injections are called plutons once they are crystallized. These activity that makes up the batholiths, that makes up each individual magma body to kind of merge with each other, typically last millions of years. For example, the Idaho batholith formation lasted about 40 million years, ending about 53 million years ago. Batholiths are typically named are typically considered batholiths if they are at least 100 kilometers squared. If they are smaller than that, the plutons that appear are typically named stocks. Okay, so you see that name right here as well. Stocks are basically one single magma chamber, or maybe 2 of them, but not amounting to be 100 kilometers squared. Laccoliths, as you're seeing right here, they appear right here, and when crystallized right here, are intrusions that can lift the sedimentary strata into which they penetrate. So you're seeing, for example, it's a little easier to see in this picture on the left, but they are being inserted in between layers, and they're pushing that structure upwards, that sedimentary structure upwards. Many of them have been found in southern Utah, which is I think the closest ones where laccoliths are common. Lastly, it is common to see xenoliths inside intrusive igneous bodies, possibly in the process of assimilation. So xenoliths are pieces of dislodged material that did not melt fully inside of the magma chamber, for example. But xenoliths are much smaller features, not these huge features like the ones that I've mentioned before in this slide. So xenoliths tend to be on the order of centimeters to meters, nothing too big. But you do clearly see that they are of a different chemistry and of a different nature than the surrounding rock. For the remaining of the lecture, we're going to look at igneous rocks and mineral resources. So in the recent years, there has been an exponential increase in the demand for metals due to the growth in population, obviously, of the planet, and the growth of the middle class more specifically. Some of the accumulations of metals such as gold, silver, copper, mercury, lead, platinum, and nickel are produced by igneous processes. Therefore, knowing how and where these important materials are likely to be concentrated is vital to our well-being as a species. Table 4.1 in your book is a great summarization of the occurrences of these metallic minerals, if you are curious, and you'll see that many of them are caused by igneous processes, so I encourage you to check it out. So as I had mentioned before, crystal settling is one of the ways in which rare metals can become accessory minerals of the more felsic magma bodies. Crystallization in a fluid-rich environment that is constrained, where ion migration is enhanced, results in the formation of crystals of several centimeters or even meters in length. This type of rocks are called pegmatites, as we kind of covered the pegmatitic texture a little bit before. Crystals of muscovite, feldspar, quartz, the size of houses even, have been found in North Carolina and in Ontario, for example. And although they are not the norm, typically these crystals don't grow to that size, it does give us an idea of the types of environments required for the formation of these rocks containing the precious metals. Some magnetites are found to have lithium, cesium, uranium, and rarer elements, as well as gems such as tourmaline, beryl, and topaz. Lastly, not all late-stage magmas produce pegmatites, and not all pegmatites are solely rich in lighter ions. So remember how most of the remaining melt within a magma body tends to be felsic? Well, not all of the pegmatites that result are from this felsic composition. Some of them tend to have heavier ions as well, forming their minerals. For example, in Kiruna in Sweden, a magma composed of over 60% magnetite, which is a very heavy mineral, produced one of the largest iron deposits in the world.